Welcome to the Guards Riddle, an interactive puzzle that teaches one of the most fundamental ideas in computer science, backtracking search. In this video, we'll watch a computer solve this puzzle step by step, from the simplest level all the way up to level 8. Along the way, you'll see exactly how a computer thinks when it's tackling a problem that has no obvious shortcut. Here's how the puzzle works. The guards standing in the top row are numbered by rank. Each rank appears exactly twice. Your goal is to drag them into the yellow boxes at the bottom. But there is one rule: two guards of the same rank must be placed exactly that many boxes apart. Rank 1 guards, 1 box apart. Rank 2 guards, 2 boxes apart. Rank 3, 3 apart, and so on. The instruction table shows a complete solution for n equals 4, 4, 1, 1, 3, 4, 2, 3, 2. Check rank 1, positions 2 and 3, gap of 1. Correct. Check rank 4, positions 1 and 5, gap of 4. Correct. Every pair satisfies the rule. Let's start with n equals 3. 3 pairs of guards, 6 boxes. I'll click Auto Solve. Watch the color coding. Green boxes are being tested right now. Blue boxes are confirmed placements on the current path, and pink means the computer just backtracked. It gave up on that choice. Rank 1 locks in green flash. Now rank 2 tries different positions. Rank 3 needs to fit, it can't. Pink flash. Backtrack, try the next option. Still can't fit rank 3. Pink again. After exhausting every possibility, no solution exists for n equals 3. The computer didn't just fail to find one, it mathematically proved that none can exist. Level 4. 8 boxes, 4 ranks. Watch rank 1 snap in blue. Rank 2 tries its first option, works so far. Rank 3, rank 4 is searching there. The board reads 4, 1, 1, 3, 4, 2, 3, 2. All boxes light up gold. The dialog confirms, solution found. Notice the tries and backtracks counters. The computer explored only a small fraction of all possible arrangements before succeeding. That's the power of backtracking. It abandons dead ends early. For 8 positions, brute force would require checking over 40,000 combinations. Backtracking finds it in far fewer steps. Level 5, 10 boxes, 5 ranks. A bigger search space. Notice how much more backtracking happens now. The computer places the first few ranks confidently, then hits a wall fitting the next rank and has to unwind its choices, sometimes several levels back. Each pink flash is the computer saying, "This path leads nowhere, I'll try something else." The solution: 2, 3, 2, 5, 3, 4, 1, 1, 5, 4. Rank 5 at positions 4 and 9, gap of 5. Verified. For n equals 6, no solution. Watch the backtrack counter climb much higher than before. The search space is larger, the computer works harder, but the answer is the same. No valid arrangement exists. For n equals 7, no solution again. An even larger search, even more backtracks. The computer proves impossibility by exhaustively checking every branch of the decision tree. Here's a pattern worth noticing. Solutions at 3 through 8 only appear at n equals 4, 5, and 8. What do those numbers have in common? Pause the video and think before we reveal it. Level 8, 16 boxes, the most complex level in this puzzle. I'll run this at high speed so we can see the full process. Watch the step counter. Hundreds of steps, green, blue, pink, green again. The solver is navigating a tree of decisions, pruning branches that can't possibly lead anywhere useful. And solution found. Look at the backtrack count compared to level 4. The search was far more expensive, showing how computational cost grows with problem size. The full arrangement: 1, 1, 2, 8, 2, 3, 7, 5, 3, 6, 4, 5, 8, 4, 7, 6. The solutions appear at n equals 4, 5, and 8. All leave remainder 0 or 3 when divided by 4. Backtracking is the same core algorithm that powers Sudoku solvers, chess engines, and constraint-satisfaction problems across computer science. Now it's your turn. Use one step to explore each decision by hand, or try dragging the guards yourself. Can you solve level 8 before the computer does? Good luck.